The reason we have simple machines is simply to make work easier. For some reason, this boy wants to lift the cheetah to the top of the table. Unfortunately, the cheetah is pretty heavy, and it's difficult for him to lift. When lifting the cheetah, the boy has to apply the same amount of force that's equal to the weight of the cheetah. So, the heavier the cheetah, the more force he has to apply to lift it. To make it easier to lift the cheetah, the boy decides to use a ramp. Look how easily he pushes it up the ramp. The ramp, a simple machine, takes some of the weight of the cheetah and makes it much easier to lift. Mechanical advantage is a term that describes how much easier a simple machine makes the work that we do. Simple machines are designed to make work easier, so how much easier or faster that machine makes your work is the mechanical advantage of the machine. When a machine takes a small input force and turns it into a larger output force, we say that the machine gives us a mechanical advantage. A mechanical advantage is a machine taking a small input force and turning it into a large output force. Since we know that's what's happening, we can calculate exactly how much of an advantage that gives us. In other words, a mechanical advantage of 2 means that the machine makes work 2 times easier. For all simple machines, we have to calculate some sort of force, the input force, to allow the load or object to move or change. The force on the load is what we call the output force. In other words, to get the greatest mechanical advantage, we want to apply the smallest force we can in to get the greatest force we can out. So if we want to calculate mechanical advantage, we need to know what exactly it is. Mathematically, we define it as the ratio of the output force to the input force. So, MA, or mechanical advantage, has no units, because it is a force, the output force in newtons, divided by another force, the input force, also in newtons. This formula for mechanical advantage, MA equals FO over FI, relies on being able to measure the forces when using the machine to do work. Sometimes, however, we don't know the forces that are applied in a given situation, or we cannot measure them. This is important, so make sure you take it down. Mechanical advantage, MA, is the ratio of the output force divided by the input force. With some simple machines, we can use a shortcut to calculate the mechanical advantage. This mechanical advantage would be the one of the machine, and it does not depend on the actual load we're using. We refer to this as the ideal mechanical advantage. When using the machine, often there are losses because of friction. The actual mechanical advantage, calculated using forces, is the one that takes into account what actually occurs and any energy that's lost. It'll be equal to or less than this ideal mechanical advantage, since this would be the one that the machine would provide if there was no energy lost. The actual mechanical advantage is the ideal one minus any forces lost due to friction, slippage, and distortion. Let's look at the first simple machine, a lever. To calculate the ideal mechanical advantage of a lever, we compare the length of the effort arm with the length of the load arm. The ideal mechanical advantage is the maximum that could be achieved from the lever if there was no loss of energy. This is important, so be sure you take it down. The ideal mechanical advantage of a lever is the length of the effort arm divided by the length of the load arm. The units aren't important as long as they're the same. Let's look at our first sample problem. What's the mechanical advantage of the wheelbarrow in the picture shown? When solving a problem, the first thing we do is list all our given information. So, the effort arm length is 120 centimeters. The load arm length from the picture is 40 centimeters. Then we identify what we're trying to find, which is the ideal mechanical advantage, or IMA. So IMA equals question mark. Next, we write out the formula that we're going to use, or we analyze our situation. So, ideal mechanical advantage of a lever equals the length of the effort arm divided by the length of a load arm. Then we substitute in our values, 120 centimeters divided by 40 centimeters. We solve to give us 3. Because both are centimeters, the units divide out. And then, don't ever forget your final statement. The ideal mechanical advantage of the wheelbarrow is 3, which means the wheelbarrow makes our work 3 times easier. Let's look at the next simple machine, a pulley. To calculate the ideal mechanical advantage of a pulley, we compare distances or lengths of rope over which we apply the force. So, the ideal mechanical advantage of a pulley is the input distance, in other words, how much I have to pull the rope, divided by the output distance, in other words, how far the load actually moves. This is a single fixed pulley. It's attached to the wall above and doesn't move. To lift the object 20 centimeters, the rope must be pulled 20 centimeters. So, a single fixed pulley has a mechanical advantage of 1. Why do you think, then, we would use a single pulley? Now let's do a sample problem with pulleys. To lift a load 5 centimeters with a pulley system, 15 centimeters of rope needed to be pulled. What's the mechanical advantage of the pulley system? Actually, this should be the ideal mechanical advantage. So first, we list what we know. The input distance equals 15 centimeters. The output distance, how far the load was lifted, equals 5 centimeters. What are we trying to find? The mechanical advantage. Output distance is 5 centimeters. Mechanical advantage equals question mark. It should be ideal mechanical advantage in this case because we don't have forces. So for a pulley, our ideal mechanical advantage equals the input distance divided by the output distance substituting in, we get 15 centimeters divided by 5 centimeters, which gives us a mechanical advantage of 3. Again, the units divide out. Our final statement, the pulley system has a mechanical advantage of 3.